So, a while ago, I published a video of a concept for a rotor with cyclic pitch control based on a rotation compensator. Basically, if you want to control a rotor with a swash plate, like helicopters do, you need to attach the plate to a non-spinning thing under your rotor. For a helicopter, that is the fuselage. The goal here is to fly with no fuselage and no tail rotor for torque compensation. In the description you will find the video that explains the details of the concept and that shows its workings in a lab setting. Well, it is taking a bit longer than I hoped to build the actual rotor, but since we completed the first successful, short flight, I thought I would share an update. The rotor in the video is designed to be used both in a pumping cycle and torque-based airborne wind energy system. For testing purposes, it is not attached to either of the two, so no electric energy is being generated. With the first flight, I believe we have finally eradicated most of my stupid mistakes in the hardware, and Daniel can start to fine-tune the controls. We will fix the rotor, get a taller ladder, continue the testing, and present the details of the control system on this year's Airborne Wind Energy Conference. If you are an expert for rotor dynamics and have theories for some of the effects that can be observed in the video, I would love to hear from you. There are three things that I would like to understand. For the whole flight, the maximum pitch was at the 6 o'clock position with constant amplitude. So here are my three questions. Question number one. Gyroscopic precession makes me think we would have to turn maximum pitch to the 9 o'clock position by 90 degrees. This does not seem to be the case. Why? Question number two. Whenever the wind speed increases, the rotor axis seems to first turn horizontal before suddenly going up. Why? Question number three. After going up, the rotor seems to spontaneously, and violently so, turn side and downward, maybe in a circle. Again, why? We are adding code that detects the sideways drift and will counteract by changing the phase of the cyclic pitch, but it would be nice to understand the physics of what's happening a bit better. If you have an answer to any of the three questions, please leave your thoughts in the comments and or send me a message. This work is brought to you by Team Tüdelpower, with most of the heavy lifting actually being done by Daniel during his master thesis of the control system, and now during the field testing and improvements here going on in Spain right now. Thanks for watching.